Hey folks, as promised in this video, you're going to learn about the math of standing waves. So by the end of the video, you will in fact be able to solve some problems involving standing waves. So let's go ahead and get started. So the key question that we're going to be kind of focusing on as we work through this video is, are the ends of my wave nodes or antinodes? So our standing waves are often going to be generated on either a string or in a tube. So we have to think, do we have nodes or antinodes at each end? I'm going to be looking at three key kinds of standing waves, three key ways in which they're generated. And this question is going to be the focus of how we find our standing wave equations. So let's start with a wave on a string, because I think that's the simplest example to think about conceptually. So good examples of waves on strings are guitars, as you can see in the picture on the right here. Other good examples are violins, violas, cellos, and of course the classic pulling a rubber band between two of your fingers and strumming it with a third. So with a string, I know that each end of my string has to be a node. And I know this because the ends of my string are attached down to something, so they can't move around freely. So what that means is that any wave that's created, any standing wave created on the string is going to have a node at each end. So I can create a standing wave like so, where my string is vibrating up and down, and the center of my string is an antinode. I can also create a wave, however, shaped like this, where I have a node on both ends and an additional node in the center of my string. Similarly, I could draw a third waveform like this. Or excuse me, I actually messed that up a little bit. Let me try one more time. So I could draw a third waveform like so. Again, I have nodes on each end and an antinode in the middle, but I have two additional nodes, each one about a third of the way down the string. So what this means is that there are multiple waveforms that can fit on my string, so that my string can generate multiple standing waves. Let's figure out the frequency of those standing waves. So let's take a look at our red wave. So here, if I were to continue expanding out my wave, so I had a full waveform, what I would get is that if I define the length of my string as L, I know that my red wave, what we call my fundamental frequency, is twice the wavelength of L. So L is equal to 1/2 of the wavelength of my red wave. And that's because, of course, a full wavelength looks like this. And for my fundamental frequency, the only part of my wave that's actually on the string is that first half. Now I also know that the speed of the wave on the string is equal to f times lambda, the frequency of the wave times its wavelength. I can rewrite that as frequency is equal to v over lambda. And knowing that lambda is equal to 2 times the length of my wave, I can then say that frequency is equal to v over 2 lambda. If I do the same thing for my second wave, what I know is that the length of my string is equal to lambda, or frequency is equal to 2v over 2 lambda. I could simplify that to v over lambda, but I'm not going to because I want you to see the pattern here. And because the third wavelength that I can fit has a length, or my length is equal to 3/2 of my wavelength, because I have 3 half wavelengths here within the length of my string. Or if I wanted to write this a little differently, I would write that lambda, and I messed up here, guys. I wrote a lambda instead of an L. So I would write that lambda is equal to 2/3 of L. And you can see that, of course, in my picture, where my wavelength takes up 2/3 of the length of my string. So putting that in my frequency equation, what I get is that my frequency is equal to V over 2/3 of L, or frequency is equal to 3V over 2L. So looking at my pattern, I have my fundamental frequency, which is 1V over 2L. I have my second frequency, which is 2V over 2L, and my third harmonic frequency, which is 3V over 2L. So the way that I will simplify this into an equation that's useful for any harmonic, so any wave that fits on my string, is I can say that frequency is equal to NV over 2L, where N is my harmonic number. And that number can be any real number. Actually, it can be not just any real number, it can be any integer, so any whole number. So our fundamental frequency is when N is 1, but N could also be 2, 3, 4, 5, 6, and it will still fit on my string. Now let's look at a very similar example, and that's an open tube. So a good example of an open tube is a flute. And if I draw my open tube, what I'll see is that at each end, I need to have an antinode, because I need to have my maximum displacement, my maximum energy at each end. So the fundamental frequency, the smallest wave I can fit here, is going to look like this, waving up and down at its maximum, at its antinodes at each end, and with a node in the middle. My second harmonic frequency is going to look like this, with again an antinode at each end, and now an antinode in the middle as well. And my third, and I'm going to go ahead and actually draw this as a solid line instead of a dotted line, because I think it makes it a little easier to see, makes this a little bit less of a busy picture. And I'm going to do the same with my third harmonic frequency. And as you could tell, guys, I always have a little bit of a hard time with my third harmonic frequencies. So I actually paused the video for a little bit so I could actually practice drawing my third harmonic frequency. Here it is. It's a hard one. This is the kind of thing that I have a hard time with. So looking at our first harmonic, we have this much of a wave. And we know that the wave would continue like so. So we've got exactly half of a wave again. So I know that the wavelength of my wave is 2 times the length of my pipe. And then again, I can write V equals F lambda, and frequency is equal to V over lambda, or frequency is equal to V over 2L. With my blue frequency, I can see that I have one full wavelength. I go up, down, and back up. So lambda is equal to L, and my frequency is equal to 2V over 2L. Similarly, in my green equation, lambda is equal to 2/3 of L, and my frequency is equal to 3V over 2L. I'm not going to go through this, through the math here, guys, but I think if you guys were to look back at the last slide, you'd be able to see how that math all works out. So again, for my tube, my general equation is going to be NV over 2L, where again, N is my frequency, or is my harmonic, excuse me. So am I looking for my first, second, third, fourth harmonic? And is of course going to be an integer. And then V over 2L, V is my wave speed, frequency is the frequency of the produced wave, and L is the length of my tube. So as you can see, this is the exact same equation that we got for a wave on a string. And it makes sense, right? Both the wave on the string and the wave on the tube have symmetry, in an open tube, have symmetry, where the wave on the string has a node at each end and the wave in the tube has an antinode at each end. So for our last one, we'll be looking at an asymmetrical situation. So we're going to be looking at the closed tube, where we have a closure on one end and then an opening at the other. One example of this is the clarinet, and in fact, most wind instruments are closed tubes, where one end is closed off by the player, the musician, and the other end is open, and is where sound comes out. So I can simplify this by drawing my closed. So I know that the end of my closed tube is going to, the closed end of my tube is going to be a node, and the open end is going to be an antinode. The antinode we've talked about, the node is because that is where my wave is reflected, and so we're going to have an antinode, or we're going to have a node on my closed end. So the first waveform that can fit there is this. And again, it's wave moving up and down, and so we represent that by drawing both sides of the wave. Now my second frequency is again going to be open at one end and closed at the other, like so. And my third is going to look similar, like that. So looking at my first harmonic frequency, that red line, I can see that I have 1/4 of a wave. So I have that part of a wave. My wave is going to continue down like so, down to the negative and back up to 0. So I know that the wavelength of my wave is 4 times the length of my tube. Again, I can say that V is equal to F lambda, and therefore frequency is equal to V over lambda. And I'll say that frequency then is equal to V over 4L. Let's do the blue tube now. So this one we can see. So my blue wave I can see is 3/4 of a wavelength, because my wave goes up and down and is just missing the part where it comes back up again. So that means that lambda is equal to 4/3 of L, because 3/4 of my wave is in my tube. And again, L is the length of my tube. So putting that into my equation, I know that the frequency then is equal to V over 4/3 of L, or my frequency is equal to 3V over 4L for my next harmonic. For my last harmonic, lambda is equal to 4/5 of L, because I can fit 1 1/4 wavelengths, or 5/4 of a wavelength, into my tube. So that means that the frequency produced by the tube at this point is going to be 5V over 4L. So again, I can simplify this by saying then that my frequency at any given harmonic is equal to NV over 4L. But N in this situation, you could see, has to be odd. So no even numbers for N. So there you go. That is the equation for the wave in a closed tube. And this is going to be our situation for any asymmetrical situation. So all three of these equations are equations you need to know. But thankfully, for a string and an open pipe, the equation is the exact same and is pretty simple. With a little more complexity with a closed pipe, because our because our pipe is not symmetrical, and therefore we have to use NV over 4L and can only include odd numbers versus being able to use any harmonic, so for second, third versus first, third, and fifth, and dividing by 2 instead of 4. So takeaways. The waves that can exist on a string or in a pipe are dependent on the boundary conditions of that medium, so whether we have nodes or antinodes at either end. And the standing wave frequencies that can exist in a medium depend on the length of that medium. So we can actually calculate things like the speed of sound by just measuring the frequency and the length at which we get our resonance frequency. So the length at which our tube can resonate with a known frequency. So that's a pretty cool application of this. Anywho, I'm going to go ahead and let you guys try solving some problems on your own. Best of luck and happy solving.